Hello, welcome to this tutorial. I'm going to show you how to solve first question for the CS3340 sample midterm. Starting with 1a, let's look at these pair of functions that were given. We have n and n plus n over log 2n. Alright, let me just write them here. Alright, so this is question 1, so I'm just going to write that here. Okay, so the first thing we need to notice, so we kind of have to pick one of omega, O, and theta. Theta is more general than the other two, but looking at this, we can see that n appears over here. So we're adding something to that n, so intuitively we know that this is going to be less than or equal to that, right? In big O notation, this is to say n is dominated by n plus n over log 2n. Okay, so we can stop here, but that's partially correct. There is more that we can do. Notice that this on the right over here, we can make it smaller than some constant multiplied by n. To see this, let's actually write this n plus n over log 2n. Now we're dividing by some number log 2n, and log 2n is bigger than 1 for n greater or equal to 2. So let me just write that down. N greater or equal to 2 implies log 2n is greater or equal to 1. So if you divide by a number greater than 1, then this becomes smaller than n. Now, if that's the case, then we have this is less than or equal to n. Okay? Or sorry, 2n. Now, when this happens, that means we get this where n plus n over log 2n is in big O of n. This written equivalently, if we reverse the order, this is to say n is in big omega of n plus n over log 2n. So these two are saying exactly the same thing. Just when you reverse the order, you replace the O with omega. Okay, but by definition of big theta, when you have something like that, so we have already proven this part, then this part. So you have n is big O of something, n is big omega of something, then the combination of those two imply that n is in big theta of n plus n over log 2n. Okay, so this would be the answer for the first question over here. Okay, so this is big theta. Alright, so then for the next question we have n plus root n and n. Okay, so let's see. Question 2. n plus root n. As with previously, we said we have n here and it's n, added something to it. Of course, this is going to be less than or equal to that one. Okay, so that means n is big O of n plus root n. That's not enough. We can consider when root n, so actually let me write that here. So n plus root n, this is obviously less than or equal to n plus n. Why? Because root n makes numbers smaller. If we consider 4, for example, right? Root of 4 is equal to 2. So you can see 4 shrunk to 2. Root 16 becomes 4, and so on. So obviously, when you remove the square root, this thing is bigger. Okay, this in fact only holds for numbers, maybe you can write that for all n greater or equal to 1. Okay, so when this happens, this is obviously 2n. That means n plus root n is in big O of 2n, or of course, you know, constants don't matter. So if we write this equivalently, then we have n is in big omega of n plus root n. So combining this one with this one here, we get n is in big theta of n plus root n. Okay, looking at the next question. Well, actually, let me just write that down. We have n times log 2n squared and n to the log 2n. So let's write them down. Wow, I already forgot. n log 2n, n log 2n squared. And the other one was, I believe, I don't remember actually. N to the log 2n. Okay. So for this question, without going into deep mathematics, I'll try to use intuition to explain why my answer is the way it is. So, first of all, we can actually simplify this a little bit. We could write n 2n log 2n. Basically, whenever you have log n to the power something, you can always take that power outside and multiply it by the term. Okay, compared to n log 2n. Now, what I want you to imagine with me right now is, forget about constants. So let's look at, in general, Cn log 2n, and then we have, again, let's put a C here. That's not necessarily the same one, so maybe let's just put D. Dn log to the power of log 2n. In general, as we increase n, so let n go to infinity, notice that we have n to power something, whereas here we have n to power 1. Okay. Now, of course, the difference is that this n is multiplied by some number, while this n is not multiplied by a number that is a function of n. Okay? So, maybe even let me just forget about these because they're probably confusing. So, yeah, let's look at those two here. As n goes to infinity, this is the exponent keeps increasing as well, because log 2n is increasing in n. So if you want to imagine powers of 2, right? So we have 2 to the 1, 2 to the 2, 2 to the 3, and up to 2 to the k. So you take the log, we get 1, we get 2, we get 3, up to k. So you can see that the log keeps increasing as well as n increases. Okay? But 1 does not increase. That's just 1 forever. Now, on the other hand, this is just multiplied by some number log 2n. So what do you think makes something bigger, multiplication or exponentiation? And the answer to this is obviously exponentiation. So, if you want some more intuition, let's look at n times 1, n times 2, n times 3, and so on, up until n times k, compared to n to the 1, n to the 2, n to the 3, until n to the k. So put in any number you want that is positive, of course, and probably greater than 1. What you'll notice is that exponentiation is always faster. So in our case, this function is always faster than the one over here. So we can say that n log 2n squared is less than or equal to n to the log 2n. And of course, from that we can conclude that this is a big O relationship. Okay, so you can just, or I'm just going to rewrite this. So that's this one, big O. Now, for the same reason explained below, we cannot reverse the relationship and conclude that, this is smaller than the one on the left. The reason is because exponentiation is faster than multiplication. Okay, and you can see that we are in here. It's log 2n and it's log 2n, right? So if this log is kind of confusing, what we can do is make it something else. But it wouldn't really change the matter. It's just that we're multiplying by the same thing and we're exponentiating by the same thing. Of course, ignoring constants. we can see that, of course, exponentiation is always faster. But if this is not clear, you could write it as some function, which is big O. I don't want to use big O a lot, so let me just write it without big O. So you have n log, you have n, some function fn, okay, and there we had n to the fn. And of course, fn increasing is an increasing function. Then in this case, without a doubt, exponentiation is faster, okay? So we have n times fn less than or equal to n to the fn, where fn is increasing function. If fn is decreasing, this might not hold. So we should not, we should pay attention to whether f is increasing or decreasing. But in terms of log, then log is always increasing. So this holds, and we conclude that nfn is big O of n to the fn. Okay, but we cannot have the omega. This is, exponentiation is faster. Okay, so we have big O. Next question is 2 over 3 to the n compared to n. So we have 2 over 3 to the n compared to n. And again, we have a case of exponentiation versus the identity, which, if you want to think about, it's kind of like multiplication, right? Either way, there is no doubt that exponentiation is faster. But let's actually look at what's happening here. This is 2 over 3, which is less than 1, correct? Of course, 2 is less than 3, so that means this number is less than 1. If it's less than 1, then exponentiation is decreasing, right? When you exponentiate by n, you get a smaller number. Let's test that out. So 2 to the 3 to the power 1, 2 to the 3. Now 2 over 3 power 2 is 4 over 9. Okay, so no, I cannot cancel out anything. But if you actually evaluate this in the calculator, you'll notice that as we increase n, you'll approach 0. Okay, so maybe you could use decimals if you want. Okay, so maybe you want to graph that. Quite slow. Okay, so 2 over 3 to the n, and this is, call it y. Okay, see, as n increases, this just goes to 0. Whereas n, it increases, okay? That one is increasing. So asymptotically speaking, even though this is exponentiation, because the base is less than 1, then here exponentiation is decreasing. So this is less than or equal to n, okay? For all n you want. Now, of course, n has to be positive. So we can say that then 2 over 3 n is in big O of n. So notice it's really important to look at whether a function is increasing or decreasing. We can't just say exponentiation is faster than multiplication and that's just it. But you have to think more. You have to think, well, as we exponentiate, does the number get bigger or smaller? Well, if it gets smaller, then that's kind of the opposite of what we want, okay? So that's why 2 over 3n is big O n. Now, can we do the other way around? Of course not. There is nothing that could make up for because exponentiation is so fast, there is no constant that we could multiply that would make it big enough to match up with n, okay? So that's just basically why it's only big O and nothing else. Okay. The next thing is looking at 2 to the n compared to 3 over 2 to the n. All right. Now, let's see. This is the base here is what? Bigger than the base here, right? Because if you increase this by 1, we get 4 over 2, and this is actually the same if this was 4. But now that this is 3 over here, then this is smaller. The one on the right is smaller than the one on the left. When this holds, then we can obviously see that this is going to be greater than the one on the right, and we cannot say the other way around. Exponentiation is fast, but the base also determines how fast. Okay, so as the base increases, then this becomes faster. So, you know, if you have like b to the n and c to the n, now which one is faster? The faster would be determined by the base. When the base is bigger, then, so if b greater than c implies that b to the n is faster. Okay? Other way around, then bc is faster. But since this is the case, since this is faster, then we can say that 3 over 2 to the n is in big O of 2 to the n. But that's not the same order that we're given. Okay? To reverse the order, we use big omega. So we have 2 to the n is in big omega of 3 over 2 to the n. And okay? And that's it. We're done here. And maybe I should just look at question B quickly. So for these, you could find them in the slides, and you could just find them in the slides. What is the worst case for construct and Hoffman coding tree? This is n log n. What is the average case for the quicksort? This one is big O n log n. What is the worst case time complexity for heap construction? Well, for heap construction, this was big O n. If you look at the bottom-up approach. What is the worst case time complexity for, I actually don't know what he's asking here. This is nonsense to me. You could email him. What is the lower bound for sorting based on comparison? This is omega n log n. These can all be found in the slides, so you could see detailed explanation as to why. Alright, so hopefully this was useful, and see you in another video.